As is customary, first of all, thank you, Danny. Great talk. And thank you all for coming to or sticking around for my talk and bearing with me while I had my little glitch on my audio visual. As is customary, this second slide is going to be a quick about me and a quick highlight reel of my credentials. My name is Trevor Grant. I am from the Humboldt Park neighborhood of Chicago. This screen background is a picture from the sledding hill. It's the skyline, and around sundown, you get this cool little thing where all the buildings light up orange in December and January, and I thought it looked neat. First and foremost, I'm PMC chair of Apache Mahout, and while not the second most important thing, a fun fact, I'm on the project, also on the project mentorship committees of Apache Streams, Apache Community Development, and I'm a mentor of Apache SDAP Incubating. All cool projects, please check them out. From all of this Apache activity, you might have guessed I'm also a member of the Apache Software Foundation, but wait, there's more. I'm author of Kubeflow for Machine Learning from Lab to Production. And you might have guessed, I'm sorry. And lastly, since I believe our work shouldn't define us, my side hustle is I'm trying to start importing e-trikes to Chicago. Haven't decided on a name yet. And finally, I'm director of developer relations at Arrikto. And even though my work at Arrikto was last, it's certainly not least. It's a segue into about Arrikto. It's also customary for the third slide to be about who pays me. The thing to note here is we're hiring developer relations engineers. Imagine getting paid to play with open source, write blogs, and give talks. Please apply. We're specifically looking for candidates in Europe, Asia, and the West Coast of North America. So during the lockdown, my interests have migrated a lot into storytelling, and the real benefactors / victims will be you, the guinea pigs who will watch this, a technology talk in 3 acts. In the first act, we'll do some exposition, introduce our characters, set up our problem a bit. In the second act, we'll dive more deeply into the problem. And finally, in the third act, which I hope will be the majority of the talk, we'll talk about how the characters work together to solve the problem. There will also be a brief epilogue where we discuss some of the results and outcomes of the research. So we begin with a bit of exposition and introduce our characters and our problem. The characters on this adventure will be Kubernetes, Kubeflow, Apache Spark, and Apache Mahout, a motley crew indeed, born in different generations to solve similar but slightly different problems. Kubernetes, what is it? Kubernetes is a portable, extensible, open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. It has a large, rapidly growing ecosystem. Kubernetes services support tools and are widely available. That is directly from the Kubernetes website. This is my favorite works on my machine meme, but we're not going to be using just one machine, e.g. Docker, like in the meme. We're going to be using multiple, and Kubernetes helps keep track of them for us. So we're using Kubernetes to make this easily reproducible for others. Design once, run anywhere. Kubernetes is a de facto container orchestration layer. Note I said de facto, not the only. Works on-prem or any serious cloud, GCP, AWS, Azure, IBM Cloud, DigitalOcean, the list goes on. Note, I am grossly underestimating the power and usefulness of Kubernetes here. I don't want any Kubernetes contributors egging my house. So please, if you're not familiar with Kubernetes, go see other talks and learn more and get familiar. It's an amazing technology. And secondly, we're using Kubernetes because we want to use Kubeflow. What is Kubeflow? Also directly from the project website, since Jimmy gave a good opening on this earlier. The Kubeflow project is dedicated to making deployments of machine learning workflows on Kubernetes simple, portable, and scalable. Our goal is not to recreate other services, but to provide a straightforward way to deploy the best of breed open source systems for machine learning to diverse infrastructures. Anywhere you are running Kubernetes, you should be able to run Kubeflow. Why do we need it? More succinctly, Kubeflow lets us do all this work, then post our pipeline, and then anyone else can reproduce our work by going to fetch the data we used, cloning our notebooks and pipeline, and uploading and running their deployment. Or if they want to extend our work, for instance, doing some deep learning at the end, then they do all those steps and just add a step at the end for whatever magic they want to tack on. Or if they want to use our system to denoise other CT scans, they just need to put scans in a directory mimicking the structure of our input data, or other combinations too. The point is, Kubeflow makes it much easier to reproduce research, and there are lots of other talks about why that's important. Grumpy Cat doesn't like to reproduce research, and neither do graduate students, but that's how science works and also how graduate programs work. I'm just tangentially touching on this. There's an entire talk here about why reproducible research is good, why Kubeflow is great for making findings reproducible, extensible, and why people should not only post their code with papers, but also full pipelines, since pre-processing steps are another reason sometimes papers can't be reproduced. Okay, so that ends this soapbox, but there will be more, I promise. Also from the website, Apache Spark is a multi-language engine for executing data engineering, data science, and machine learning on single node machines or clusters. While still exciting and new, it's a bit more of a mature tech. And since you're a lean-in technologist, I'm going to assume a bit of familiarity here. The first reason we need it is when we start working with CT scans, they're big, like 500 megabytes. And when we try to do a matrix inversion, which we'll talk about more in the next section, to do so on a single node in NumPy was estimated that you need about 500 gigabytes of RAM. Some computers do have that now, but it's a pretty harsh requirement. Using Spark lets multiple smaller machines work together, which again, more people have access to, costs less to do work on. And we want this to be easily reproducible by anyone, not just big corporations and universities. But no, we're only using Spark for the layer that lets multiple nodes work together. The actual matrix math, we'll be using a library called Apache Mahout from the website. Apache Mahout is a distributed linear algebra framework and mathematically expressive Scala DSL designed to let mathematicians, statisticians, and data scientists implement their own algorithms. And you might be thinking, wait, I've heard of Mahout, but I was thinking it was something else. I'm confused. Well, I happen to be the PMC chair of the project, which is one of the leaders who gets stuck filing the quarterly reports. As such, let me take a moment to clarify. Mahout was the original distributed machine learning library. Machine learning on Hadoop and Mahout are synonymous. But then Hadoop started losing popularity to Spark and wailed on the way. And in 2014, 2015 time, a new Mahout was made, one that used Spark as a default backend and introduced a Scala domain specific language that made it look like R. That is, you could write R-like expressions in your Scala code, which are much easier to read mathematically. But now it's been another half a decade. Scala's popularity is starting to wane, and several of the project leaders are working on blockchain-related issues, either for fun or as part of our day job. I'm doing it for fun. My day job is just Kubeflow. When Mahout started, it was the first and only distributed machine learning library. Now it's just one of a nameless rabble. So recently we've decided to pivot the project into doing analytics on blockchain ledgers. For more information or to get involved, join the Mahout mailing list. So why do we need Mahout? While Spark and Mahout have some built-in functionality for dealing with matrices, they have issues with matrices that won't fit inside a single node. This isn't a problem for Spark since there aren't that many people who want to do matrix algebra anymore, but instead prefer machine learning algorithms. But Mahout has much better support, especially for distributed matrices. Specifically, we're going to need to do a matrix inversion, and I'm purposely hand-waving here since advanced linear algebra was not a prerequirement for this talk. And even if it was, I don't know how to make it interesting yet. So the takeaway is Mahout has a method called distributed stochastic singular value decomposition, which I may sometimes refer to as DS-SVD during the rest of the talk. And for our project, we need a DS-SVD. The problem our band of heroes will hope to solve will be that of COVID screening. But how? How will our heroes learn to overcome the differences and work together to solve a problem that would be way out of scope for any of them individually? Stay tuned to find out. Dun, dun, dun. The Act 2, the plot thickens. Now, you might already be thinking, why would anyone want to do any of this? Just use rapid tests. Let's do a thought exercise. Close your eyes. You're in a very large and a very empty parking lot. You see yourself walking up to a 1982 DMC DeLorean. You walk to the driver's side and open the gull wing. You sit in the driver's seat and punch into the LCD display, March 28th, 2020. You put the DeLorean in drive and start driving. You slowly accelerate, very slowly. Hopefully there's enough parking lot. Once you hit 88 miles per hour, that's about 141 kilometers per hour. You travel through time. Next thing you know, you're driving in an almost identical parking lot, just as large, just as empty, but you travel about 22 months back in time to late March 2020. It's March 2020 and people are dying. Spain, Italy, New York City, hospitals are being overrun with suspected COVID patients. Also, you can open your eyes now. You're still in March 2020 mindset, but I'm showing headlines as evidence of my points. Note the date here. It's hard to read, but it says March 28th, 2020. This guy's wearing plastic garbage bags or something as a cootie shield. It looks silly now, but at the time it was scary. Real epidemiologists then knew less than the armchair epidemiologists of today know. In March 2020, no one knew what was going to happen, but people were scared. Not everyone had COVID, and it took a long time to figure out who did and who didn't, as is shown on this piece from NPR, also on March 28th. Specifically, PCR tests, the same you get today if you get a non-rapid one, took about 3 days to return results. People were trying to come up with rapid tests, but as we see here from March 26th, only detecting 60% of true positives at the time was considered promising. Note, these weren't even widely available yet. They were more like coming soon teasers. This was compounding issues with hospitals being overrun because not everyone who comes to the hospital thinking they have COVID actually has COVID, but people had to sit there for 3 days waiting for tests to come back and possibly getting COVID during that time. Here we see an article from March 23rd. I just discovered this when making this deck, but it concisely illustrates a point. Creativity in finding new ways to rapidly detect COVID with equipment already available at the hospital was at a premium. The article refers to doctors at some of the early hotspots, Italy and Spain, using ultrasounds to make COVID I'm not going to say that word right. Using ultrasounds to diagnose COVID earlier than 3-day PCR tests could come back. Even if just directional, could have a big impact. This article from Imaging Technology News, which is admittedly biased, from February 26th, espouses CT scans for rapid COVID detection. The bias here being CT scans being called the best so early, but they are. But CT scans have issues. They actually have several issues, but the one we're going to focus on is the radiation dose you get when you get one. A thoracic CT scan, thoracic being your chest region, a thoracic CT scan gives you around 6 to 7 millisieverts of radiation. Here's a chart to put that in perspective. So it's not horrible, but it's also really high for a diagnostic procedure. As you can see in the picture, mid to high yellow. So another metric to put this in perspective, in your entire lifetime, you're really only supposed to have a maximum of 400 millisieverts of radiation. So CT scans have been used for a while to diagnose lung cancer, but full dose CT scans were also considered too much radiation for diagnostics in this realm as well. So in and around the late 90s, early aughts, a lower dose method of CT scanning was developed. An entire lecture could be given on the differences between regular CT scans and low dose CT scans, but for our purposes, allow me to hand wave a bit here. All CT scans are, in essence, a series of X-rays, which are compiled into a stack of 2D images, which can then be rendered in 3 dimensions. Low-dose CT scans use X-rays with significantly less radiation, but the resultant scans are noisier. And here you can think of noise like static on a TV with no input. Or did you ever try watching a channel when you were a kid that your parents didn't pay for? Or if you had an antenna, a channel that was just a bit too far away. You could squint your eyes and kind of get it, but it wasn't great. My hip shot recreation here doesn't truly illustrate the problem. Since the advent of, really in parallel with, low-dose CT scans, people have been coming up with ways to denoise them. The main approach in this sort of similar, the main approach is a thing sort of similar to a principal component analysis or a PCA. The thing to remember is that even in low-dose CT scans, the data set is large and cubic, not square. For instance, a 300 by 500 scan, 300 by 500, not great resolution, not horrible, but then you figure another 500 slices, and now you've got a dense matrix that has 75 million data points, or 75 million pixels in 300 by 500 by 500. PCA under the hood uses a singular value decomposition, and that's the part of the PCA that does the matrix inversion. I knew I couldn't do it locally, but as I had said earlier, I tried with NumPy. It threw a warning saying I would need about 500 gigabytes of RAM. You can get computers with 500 gigabytes of RAM, but they're pricey even to rent on cloud, and we're wizards of open source. So I'll leave that as a teaser for the next session. So to recap to this point, March 2020, there was a large need for COVID rapid tests that could utilize existing hospital equipment as opposed to having to be produced and distributed. CT scans were known to be good, but among other things, they deliver high doses of radiation. Low-dose CT scans, a technique that had been around for about 20 years, solved the radiation problems, but they produce noisy images. And through clever use of open source software and renting cloud time, we deliver a quickly and easily reproducible method for denoising CT scans, the details of which we'll go to in the next section. But first, an intermission. Well, we don't need an intermission, or we don't have time for one, so skip over that. And now for the dramatic conclusion. So to recap to this point, well, I just recapped, but March 2020, need for CT or COVID rapid tests. CT scans are good, but high radiation, low-dose CT scans create noisy images, open source. Okay, so we weren't the only ones thinking along these lines at this time. Dr. Paiva, a Brazilian radiologist, got CT scans of 10 patients with COVID from Wuhan, China, and posted them very early in the pandemic to coronacases.org to help other radiologists detect COVID with radiology. That is, to show them what it looks like. The site's still up. You can go access Corona CT scans yourself right now on coronacases.org. So what does a COVID look like in a CT scan? First, let me state very clearly that I'm not a radiologist and I have no formal training in radiology, but from the papers I've read, COVID in a thoracic CT scan presents as ground glass occlusions. And I think that's what we see here on the image, in the image on the right toward the bottom. Oops, there we go. Here. So why is it so critical to use open source software for this? I doubt I have to sell this in too hard to this audience, but in addition to open source being awesome, lots of socioeconomically disadvantaged areas need needed tests too. In March, we didn't realize how badly sub-Saharan Africa and other poor areas of the world would be left behind. But in our headlines as visual aids, we see one from January 2021 from the Wall Street Journal, how COVID-19 has widened the gap between rich and poor countries. Using open source software can level the playing field between rich and poor countries. Free and open source software can be distributed much quickly than proprietary software. I don't have time to soapbox this point out completely, but I trust you understand how, when, and why free and open source software is great. So first, let me talk about big picture, what we're going to do. It's my hope that when viewed from 10,000 meters, more intricate details will at best make more sense and at least won't bore you completely to tears. So big picture, what is going to happen here? First, we collect our images into an S3 bucket. Could be any storage. S3 bucket was what we used. Next, we have a little Python map that can read DICOM images and convert them into numerical matrices and write them back to disk. Then we load the matrices into Spark as resilient distributed data sets, or RDDs. Then we wrap the RDD into a Mahout distributed row matrix or DRM. Then we do distributed stochastic singular value decomposition, or DS-SVD, on the DRM, which yields 2 new DRMs, which we then write back to disk, and we can then render images with various amounts of denoising applied. S3 buckets aren't exactly open source, but they are lingua franca in cloud object storage. We know we've been pushing why open source is important, but also important in our solution was the ability for others to pick up and use our pipe with minimal friction. S3 buckets also aren't performant. If you're trying to do any real work loads, it would probably make more sense to do some research here and find the optimal storage for your use case. But for the first step of our pipeline requirements, a persistent volume container then downloads the DICOM from the S3 bucket to the persistent volume claim. I can't emphasize enough that this is an anti-pattern. I've recently kind of remembered why we were doing this, and I'll get into that here in a little bit. But just as a note, you can clone my repo, and you're wondering why in the world, there is an answer. Also, as another side note, since I've been revisiting this code, the CT scans on coronacases.org are hosted by some company that sells an online viewer, and they messed up the metadata. And so using those CT scans doesn't seem to work anymore. However, if you use CT scans that don't have proprietary metadata, this whole pipe in theory still should kick. Also, as a note, this whole work is published twice. The why is answered in a peer-reviewed journal article, and the how is in chapter 9 of a book, which I'll later be pushing. All of the code, as well as as well as a pipeline to deploy this on your own Kubeflow instance exists in Git, which I'm in the process of cleaning up and refreshing. There's an XCDC comic about a computer science undergrad handing in assignments in different languages. And for Python, the professor saying, you can't just import answers. Pretty much the applicable to the step. I needed to read the DICOM images. So of course, there exists not one, but multiple libraries to do in Python. PyDICOM had the easiest on-ramp, so I used it. A DICOM is also the file type of a CT scan, just as a quick bridge there. To do the next bit of magic, we needed to convert the DICOM into a numerical matrix, and PyDICOM makes that a pretty straightforward process, like 15 lines of code straightforward. So we read our DICOM process into a numerical matrix, then dumped the matrix back to the PVC. Now it's the second time I've weighed my hands and run into a PVC, but what is a PVC? A PVC is a persistent volume claim. And for those who don't know what it is, if you recall, Kubernetes is just a layer that orchestrates a bunch of Docker containers. A PVC gives you a volume you can mount to various containers. And as such, you can treat it like some persistent disk space for handing large files off between containers, or more precisely, steps in our pipeline. For instance, the first step, we requisition the PVC and download the DICOM to it. The next step, which we're on now, was to process the DICOM into a numerical matrix, then write the matrix back to the PVC. Our next step will be to read that matrix into Spark using an RDD. Now I'm making it seem like running Spark in Kubernetes is just another trivial step. Let me be clear, it's not. It's not super difficult, but it's also not super simple. If steps in our pipeline are just Docker containers, then how do we run a Spark job, which might have a variable number of workers operating across multiple nodes? In short, it requires a resource op. And candidly, so I've been digging into this more. I think the resource op is still the way to do it. You can read the manifest. We're trying to convert this into a simpler method. I'm working with some engineers at Arrikto on this. I was doing as up to as early as this morning. But for this version, which again is 2 years old and may not be the most performant, define a resource op with a manifest, like so many things in Kubernetes. And in the manifest, you specify how many workers you will use and how big each worker should be. This step is important and is what separates a real world Spark job on Kubernetes from a proof of concept where you fool yourself into thinking something which will scale, which won't. And by that, I mean, you can run, you can have a Spark step that runs on the driver node and you think, oh, cool, I'm using Spark in my pipeline. And that's fine as long as your entire job fits into your driver node. But if you need to scale out to multiple workers, it won't. You need a couple more steps in there. So that's a hack you can do, but yeah, if you try scaling it up, you'll hit out of memory errors. And as a sidebar, if you thought error tracing on Spark was bad before Spark jobs distributed on Kubernetes will be a new special layer of hack for you. So have fun with that. Also, we're running Apache Mahout on top of Spark. So we must wrap our RDD into a distributed row matrix or DRM. This whole project really didn't turn into the Mahout time to shine I had hoped. Mahout only accounts for about 7 lines of code, 1 to wrap the RDD, 3 to get some parameters, 1 to execute the DS-SVD, and then 3 to write the output. So allow me to do some more hand waving here, as we get into what a singular value decomposition is and how it works. It's easily a week of lectures in an advanced college level advanced linear algebra class. And this isn't even a full on SVD, but a distributed stochastic singular value decomposition, which was the subject of a doctoral thesis by Nathan Halko, whom I owe a beer should I ever meet him, because this technique now has powered several of my talks. So singular value decomposition will take a matrix and spit out 2 other matrices and a vector of singular values. Now, before your eyes glaze over, the 2 matrices will be, you know what, you're all at home. Supposing you're not watching, well, you're watching this live. You're all at home. If you're interested more in the mechanics of the SVD, it's fun linear algebra. Feel free to dig in. What the denoising technique in essence boils down to is a more generalized case of a principal component analysis, otherwise known as a PCA, on an image. And the idea is that the noise will be the least important vectors at the end that we'll trim off. Now, it's a gross oversimplification, but for us open source enthusiasts, It's close enough given our time constraints. So we're going to do a PCA and just trim off noise vectors at the end. Too easy, right? Couple of side questions on the slide. Why not use NumPy? I think I mentioned earlier, 500 gig of RAM. I didn't want to rent that big of a cloud. And why not use Spark's built-in linear algebra package? While Spark ML focuses more on machine learning, and the SVD method available in Spark ML is not distributed or stochastic, which will limit it to running on only one node, which gives us the same issue as NumPy. Finally, what does the image have to do with anything? I don't know. I found it on a Towards Data Science blog, so I guess data science is turning back into statistics. And this image looks cooler than my advanced linear algebra notes. So here we see some results from the paper we published on the topic. Let me be candid and say it's unclear, but unlikely the originals were low dose CT scans. However, we can see how images degrade if we denoise them too much. There's information at the bottom of how we recombine them, but recombination is a straightforward matrix multiplication problem and could be easily done in a web browser with JavaScript, though I think I use Python. And it's a typical signal and noise problem. We're doing this method remove the noise, but we can see from D down in the bottom right corner, if you remove too much noise, you also start to lose some signal. So that just about concludes my talk on using multiple open source projects and advanced mathematics to try to do some good in the world, which I have presented without a single line of code or mathematical formula. Ta-da! But wait, there's more. Epilogue. Before we published, rapid tests became cheaply and widely available, which overall is a good thing. If I had to rank things that happened in the 2020s, I'd say our book coming out was the best thing, followed by rapid tests becoming cheaply and widely available, and way down at the bottom is Zoom happy hours. I was not sad to see that trend die off. That said, go to Google Scholar and search CT scans COVID. There's still a lot of research going on and being published every day. Google thinks it's my specialty now, so they're constantly emailing me about it. I would really like to give this as a, I'd really like to give this as a full talk too. I told some jokes about in the first act, but in all seriousness, having reproducible examples is critical to modern science. And from grad school, I remember it's not always an easy thing to do. In addition to researchers not clearly defining their algorithm, not publishing data, or other inherent problems, they will often totally gloss over what data prep steps they took, which is a huge, if not the most important part of doing any analysis. This talk has a few calls to action. One of them is for researchers to help enlarge the body of knowledge by publishing not only data, but also code, full data and code, but full pipelines. Since most of the people here are probably business oriented, not academics, same rules apply, because if you build some pipeline and it's in operation for 12 months and then you go to another job, you don't want to get a call from your boss 18 months later because your old pipeline was running like a Swiss watch and it broke and no one else knew how to mess with it or knew how to fix it. So being able to easily hand off your pipeline so other people can understand it is another key feature, though often unsung feature of Kubeflow. I also touched on this earlier. Using Spark on Kubernetes, you can trick yourself into thinking something will work when really, instead of deploying a cluster, you're really only deploying a driver node. But this is a good example of how to use Spark with Kubeflow. The code for all this, yes, there is code. I just militantly don't show code in my talks. Can be found in the link shown here. But why only use this talk and code when you can buy my book and read and cite my article? Now there are, I am giving this talk at FOSDEM also on Saturday, and normally there's rules against commercial pitches at high quality talk or high quality conference venues, but I will always plug my book anyway. So great way to charm your friends and enrage your enemies. I highly recommend Kubeflow for Machine Learning from Lab to Production by on O'Reilly Media, available on Amazon. This entire example is chapter 9 of the book. It's an example chapter that goes from soup to nuts on how to build this pipeline. Another important point I hopefully don't get hissed off the stage for, we use open source so it could be almost zero cost and require no vendor, but Kubeflow can be a very complicated bear to get set up and working right. I would seriously consider some vendor managed solution. I don't mean this as a pitch for my company or any company or even just Kubeflow. Just note that you have to realize your time has value and how much of it do you really want to spend just getting to hello world? So that's my talk. Again, thanks for tuning in. I'll check Q&A for questions, and don't forget Arrikto is hiring. And if you want to work with me and get fun talks, please apply.